Previously, we have discussed the first of the two comparison tests called the direct comparison test. Next, we will learn the limit comparison test. And to get started, let's consider the following problem. And as always, we have to analyze the convergence of a given series, and here's the series, and after you check all the, whether it's telescoping, geometric, or p-series, you may come to a conclusion that the direct comparison test could be a good approach, and you may even want to compare it with this p-series, which can be easily identified from the way the original series, what it looks like. And we know that this series converges. But what's the problem with this argument? The problem is that the original series is greater than this p-series, and since the condition of the direct comparison test is very clear, either the smallest of the two has to diverge to conclude that the largest one diverges, or the larger of the two has to converge in order to conclude that the smaller one converges. So in this case, we cannot apply the direct comparison test. Why? Because once again, if something smaller converges, anything that's larger than it can also converge or may not necessarily converge. Nothing prevents it from diverging. So this is not really an example, but anti-example of a direct comparison test. Alternatively, let's consider another example. And in this example, it could be very tempting to compare this series with this p-series, and this is a p-series with p less than or equal to 1, and therefore it diverges. But why can't we draw any conclusions about the original series? Because the inequality is the wrong way. If something is less than infinity, it may be infinity, but it also still may be a finite number. So once again, the direct comparison test doesn't apply for this problem. So this is another anti-example of the direct comparison test. So what do? Sometimes you can do an integral test or some other test, but I want to introduce a new technique. Let's consider the following argument, and once again, let's consider this series, and we're going to start at 2 to make sure that all the terms are positive, and I'm going to make the following claim. I'm going to say that this series behaves exactly the same way as this series. So I'm not saying that one is greater than the other or the other way around, but I am claiming that they behave the same. That is, if one converges, the other one converges, and if one diverges, then the other one diverges. Now, If we can establish such a relation between the two series, then knowing that 1 is a p-series with p greater than 1, therefore it converges, we would be able to conclude that the original series also converges. But the question is now, what does it mean to behave the same way? Well, it can be shown that two sequences taking, and if the limits of the ratio of one sequence, in this case, let's take the general term of one sequence, and let's divide it by the general term of the other sequence. And it can be shown that if such limit is a finite number, then the two series behave the same way. So now we can just focus on this limit, simplifying the expressions on simplifying this rational expression. We can totally use the very useful theorem now and turn this into a continuous function. And this continuous function as a rational function, or we can use L'Hopital's rule a few times, but it can be easily shown that this limit is 1. So this equality can be established, and this number 1 is not infinity, so this is me writing inequality. So this number 1 is greater than 0, less than infinity, and that's what it means to say that the two series behave the same way. They kind of follow one another. They don't necessarily they don't necessarily bound each other, but they follow one another, so wherever one goes, the other one follows. And if we know that the series on the right converges, then we also conclude that the series on the left converges as well, and this type of argument is called the limit comparison test. So converges by the limit comparison test. So it may appear to be slightly more powerful than the direct comparison test, but again, it has applications. The direct comparison test has applications when the limit comparison test may not be applicable. So let's do this second anti-example. So let's once again consider the following series. And you may guess that what are we going to compare it against? We're going to compare it against this p-series, and the claim is that they behave the same. And if we can show that on the right side we have p-series with p equals to 1/3, which is less than or equal to 1, meaning that the series on the right diverges. So as soon as we can show that these two behave similarly, we'll be able to conclude that the original series diverges by the not direct limit comparison test. So now the only things left here is to convince ourselves that this is true. And to show that this is true, we have to show that the limit of the ratio of the general term of 1 over the ratio over the general term of the other one is equal to some number that is between 0 and infinity. In this case, simplifying this rational expression will give us this, but this can be easily shown to be equal to 1. So basically infinity over infinity in this case is 1, and cube root of 1 is just 1. once again, 1 is between 0 and infinity, so this is important. It cannot be infinity or 0. If it is, then you probably can use the comparison test, direct comparison test. But in this case, we were able to show that they are behaving alike, and therefore the one on the left also diverges. Let's try another example. If we can convince ourselves that this series behave the same way as this series, which is geometric, with r being 1/3, which is less than 1, meaning that it converges. If we can convince ourselves that this is true, then the original series will say it also converges by the limit comparison test. Now, to show that this is true, we're going to set up and find this limit. And it may not be too easy, but if we simplify this and divide the numerator and the denominator by 3 to the n, we can convince ourselves that this limit is equal to 2. So it doesn't matter what number it is equal to, as long as it is between 0 and infinity. The fact that the two series behave the same way is true. All right, let's do another example. So if you have something that looks crazy, yet at the same time we know it's just a rational function, which makes it easy, to recognize what it behaves like. So when n goes to infinity, we can totally ignore all the terms that are not leading term. And if we do so, then whatever's left is what we can compare our original series with. In this case, it's going to be acting similar to this series, which is actually p series with p equals 4, which is greater than 1, and therefore it converges. And we can show easily, not easily, but if we can convince ourselves that the two series behave alike, then we can use the limit comparison test. So, two things left to do. We have to establish this fact. And simplifying this rational expression and recognizing this rational function pattern here, it can be easily shown that this limit is 1, which is a number between 0 and infinity. Therefore, we can conclude that the original series converges. And the reason why is by the limit comparison test. All right, so let's summarize the limit comparison test. Which basically says that if you have two, and we're gonna keep the series positive, so if you have two positive series and the following is true, so the limit of the ratio between two general terms is equal to some number which is not 0, not infinity, then the two series made of these terms behave the same way. That is, if one converges, the other one converges, and if one diverges, then the other one diverges. So both series either converge or diverge. So those are the only two options. So a quick remark: what to do if L is 0 or L is infinity. In such a case, maybe the direct comparison test will be more appropriate, but again, it's not guaranteed. I guess instead of this, we can say then try the direct comparison test, because when it happens, the ratio of 1 is 0, the ratio of 1 over the other one is 0 infinity. That means 1 is much bigger or much smaller than the other one. So maybe you can just use the ratio test. But again, it all depends on the situation and what's given and what the series looks like. Now that we know multiple tests, we need to kind of adjust our plan, right? So our strategy. So when we have a series which we have to decide whether it converges or diverges, again, first thing we do, we check if it's geometric or telescoping or p-series. And if it is, we're done. We know exactly what to do. And in case of geometric and telescoping series, we even know how to find the limit. Now, if it's neither one of this, then we would apply the divergence test. So what is the divergence test? Well, basically, you take the nth term and find its limit as n goes to infinity. And if it's not equal to 0, then we are done. The conclusion is that the series diverges, and if the limit is equal to 0, then we are not done. We go to the next step, in which we perform one after another, if necessary, convergence tests. And as of right now, we know quite a few of them. So we know the integral test, we know the direct comparison test, and we know the limit comparison test. And sometimes it is totally possible that you are given a problem, such as this one, and it can be shown that this series converges in 3 different ways. So this series converges by the integral test. If you set up this integral, you're going to get arctan of pi over 4 and pi over 2, so which is just arctan of 1 and arctan of infinity, which give you the difference between which will give you pi over 4. So the integral test works here. The direct comparison works. You can just compare it against 1 over n squared, and because the denominator is in such a form that makes the original series less than this series, and finally, if you decide to do the limit comparison test, it will also work, and you would also be comparing it against this P series. So in such a case, you just have to have a clear strategy to decide which test is more appropriate for every given sequence. So we discussed the limit comparison test and how to use it to determine whether a given series converges or not.